Well, what's up, Logic fans? Welcome back to another video. Today we hit section 6.9 of the text, Quantificational Syntax 9. Here we explore how our quantifier rules like EI, EG, UI, UG, quantifier negation, and so on work in the context of quantificational sentences involving relations. So let's rock. Alright, so the best way to do this is just to look at some examples of valid arguments and then prove their validity, and the argument should involve lots of relational expressions, and you'll see that it behaves in a very, very similar way to just the standard property constants like FA or GB or JC. Without giving you a ton of explanation, let's just see if you can't figure this one out. So you got one premise here, and you've got the conclusion here, and your job is to prove that it's syntactically valid by producing a syntactic deduction of the conclusion from this one and only one premise. See if you can give that a shot. Pause now. Okay, so hopefully you're able to figure it out, and it's not that bad, right? And they just, again, they get treated the same way that property constants get treated. So you've got your premise here, and then it turns out that you can just, it's sort of tailor-made for De Morgan's. So you distribute this through and switch to the and, calm this out, simp it, and then you can just add whatever you like, any old sentence you like, in this case a property constant sentence. And that is perfectly fair to do. You also could have added a big, universally quantified sentence or existentially quantified sentence or another relation or whatever you like. Okay, let's look at another. Alright, in this case, you've got a single premise and a conclusion that you're supposed to deduce from it. Go ahead and see if you can't prove that this argument is syntactically valid. Pause now. Okay, and once again, it's not that bad. I mean, note that you have the leading negation in the premise, right? And that leading negation means you cannot just haul off and existentially instantiate. Remember, existential instantiation is a rule of inference and not replacement, so you have to mind this. But you can quantify or negate it and move it to the inside, right? Just like you would if this were a property constant like FA, all right? And you move it to the inside, and now you're tailor-made to universally instantiate, and since the argument wants it in terms of D, universally instantiate to D, and voila, here is the proof that this argument is syntactically valid. Here's the syntactic deduction, which shows that to be the case. Let's keep trugging along. Okay, so let's try a slightly different situation here where we have the instead of the existential quantifier, we have the universal quantifier in this premise. Pause now, give this one a try. Alright, and it's not too bad, right? So in this case, we have this leading negation, and so we still can't really use UI, but we can use QN and take it inside, and then we can go ahead and existentially instantiate to the existential pseudoname, and then we can existentially generalize on that to reach the desired conclusion in terms of Y. Alright, let's keep going. Okay, so let's try stacking multiple quantifiers and practice how our quantifier rules work with relations that have the overlapping quantifiers on them. So again, here, I think the best way to see this is via example, and my hint to you for this one is to treat it step by step. First take this one off, then take this one off, okay, and just do it in a step-by-step manner. And notice that in your conclusion, all right, you want RYY, so you might start by reverse engineering this and getting something like RVV, and that'll tell you what you should be instantiating to in each of these cases. So with that hint, pause now and see if you can get this one, and we'll come back and do it together. Alright, hopefully you were able to get it, but you just tack these off of the premise one by one. So first you tack off this one, and we're going to go to V. How do we know to go to V? Well, because we know we're going to want to existentially generalize, right? And we can existentially generalize from that, and we know it's going to be the same one in both cases. So we're going to want the RVV here in order to get this construction in 4. So first we strip off the x in terms of v, then we strip off the y in terms of v. And remember, universal instantiation allows us to universally instantiate to whatever we want, including the same thing twice, because universally quantified statements hold of everything, and so it's going to hold of the v twice, as it were. Okay, so that's a good introduction to a more sophisticated case. Let's keep sort of building a complexity here. Okay, so let's go ahead and look at a slightly harder one. So in this case, you've got the overlapping quantifiers in the premise, and you have the overlapping quantifiers on a relation in the conclusion. So we're going to have to be careful how we build the conclusion here. So in order to start this one, and rather than just starting to produce the actual syntactic deduction, what I want you to do instead is I just want you to focus on the conclusion, okay? And I want you to really think about what it would look like to reverse engineer it. And what I mean by that is, suppose you had this available, right? Strip it down of its quantifiers and sort of see what construction you're looking for if this thing had no quantifiers on it whatsoever. All right, so just sort of what rules would you apply to get it down into a particular form? Pause now and see if you can figure that much out. Okay, hopefully you were able to get it, but you know the x occurs here, and so we're going to use the universal on that because we know we're going to want to universally generalize at some point in the conclusion. So we want this conclusion here to this to be a u, and then we're left with ey ryu, and if we existentially instantiate that, then we've got the rvu. So we're looking for a construction like this from the premise. That is to say, starting with the premise, can we get from the premise to something that looks like this? Because if we can get from the premise to something that looks like this, then we'll be able to go from this back up to this, which is the desired conclusion, and that's the whole point of the reverse engineering strategy. So with that hint on this problem, see if you can't produce the syntactic deduction from the premise to the conclusion. And remember, from the premise you're trying to build something that looks like this, and then building the conclusion from that. Pause now. Okay, so hopefully you're able to get it. Here's our official syntactic deduction, and so we've got our premise, and we're going to strip off the x, and we're going to put it in terms of the v, which is what we wanted right here, right? Because that's what we wanted from our reverse engineering. It's sort of telling us, we're sort of planning in advance where we want the existential to go and where we want the universal to go. We want the existential to go on this thing right here because that's where it appears in the conclusion, and we're trying to build from this. So when we take the x off, which is already here, we want to make sure we put the v there, just sort of signal to us, aha, okay, that's where my existential is going to go, and it's going to go in terms of in terms of y, ultimately, looking at the conclusion. But yeah, so we end up with this, and then we're going to strip this quantifier off by universally instantiating it, and it's in terms of y, so it's going to go to the u, because that's what we reverse engineered from the conclusion. And aha, now that we've got this guy here, right, we know how to get from this guy, right, back to the original conclusion just by existentially instantiating and then universally instantiating, and that's exactly what we do here following it. So the whole idea of reverse engineering is to give you a plan, something to shoot for from the premise, and then once you've got it, you can get back to the conclusion, right? And that's exactly what we've laid out here, and I hope you find the technique helpful as a problem-solving strategy. Okay, in this case I would like to look at an argument that's very, very interesting. Of course, we're practicing how our syntactic rules work with relations, but here's a very, very interesting feature of relations that we noted way back in Chapter 4, and that's that all asymmetric relations are irreflexive. And so we're going to model a demonstration of that here by looking at a premise that says, hey, for all x and for all y, if rxy, then not ryx. In other words, R is asymmetric by definition, and you're going to be able to syntactically deduce from that one premise alone that R is in fact irreflexive, namely that for all x, not rxx. So you actually get to see, in practicing this particular case, a really, really interesting result, namely that all asymmetric relations are irreflexive. So before we can sort of syntactically deduce this conclusion from this premise, let's go ahead and reverse engineer the conclusion. That is to say, strip it of its quantifiers and get an idea of what it looks like devoid of all quantifiers. Pause now and do that. Okay, and it's not too bad, right? I mean, if we had the conclusion available, we might automatically universally instantiate it. And notice that if we universally instantiate, in this case, you get it's not the case that RUU. So this tells us that we should be instantiating these quantifiers to the same one both times, which is a huge clue as to how to solve the problem. So we're going to do the syntactic deduction now. You're going to go from this premise, and what you're going to try to do is get from this premise to this construction here, from which it is a very simple matter to get to the ultimate conclusion. Pause now and see if you can produce the syntactic deduction now. Okay, hopefully you're able to get this one, and there are different ways of doing it, but the clue that you need to instantiate to the same one is a big help, although there's some more work to be done after that. But here you've got the premise, okay, and we're going to try to go to that, to this construction, and it's not exactly clear how to do it, but we know we need to begin by stripping these quantifiers off. So once we do that, we get if RUU, then it's not the case that RUU. And intuitively from that, you know that therefore RUU cannot be true, right? If RUU implies that it's false, then it's got to be false that RUU. And one way, and a clever way of getting from this construction to just RUU, or rather not RUU all by itself, is to just use impla on this, and that sets up a disjunction where the left and right disjuncts are identical, and that allows you to use idempotence. And so now you've got the not RUU by itself, and you can just go ahead and universally generalize from there to the conclusion, thereby demonstrating that it's not a pure demonstration that all asymmetric relations are irreflexive, but given a particular asymmetric relation, for example, if RxY means X is taller than Y, you can then go ahead and show that for anything it's not the case that it is taller than itself. And so you can sort of repeat this for any particular asymmetric relation you're presented with, like is taller than. And you need to reverse engineer to see this, okay? And that told you that you needed to instantiate to RUU, and then from there, it was a little bit of finesse to get down to just not RUU. And you could have seen this too by if you had added not RUU or RUU, right, or not RUU, then you could imply that. So you can kind of build these things until they match as a problem-solving strategy to figure this out. So you also could have used IP. All kinds of different solutions here would have been possible, but the big hint is to make sure you use U twice. Reverse engineering lights the way on that. And so, since we're out of time, we're going to go ahead and spill over into the next video. So look for the second video on 6.9, 6.9b, quantifier rules with relations, where we'll look at some more problems and some more nifty results like this one. Roughly, that all asymmetric relations are irreflexive.